Hi there. Today we're going to look at forward Euler for the decaying case, exponentially decaying case. So this is a case you'd likely have come across last year, but I'm deliberately repeating it because I want to emphasize some of the key features, things like amplification factor, things like accuracy, that you may have encountered but that definitely need reinforcing. And then we're going to carry those concepts forward into a whole load of other more advanced methods as we go forward. Okay, so I'll hand over now to the board. And we're dealing now with our friend, the forward Euler scheme. And we're going to use this as our first example of a sort of less artificial example than the recursive example of discretizing an ODE, and then see what the stability properties and the accuracy properties are of this. So first of all, we're going to consider dx by dt is f of x. We're going to discretize this equation. And with the forward Euler, we approximate dx by dt. So first to say that our x values will go to xn, so i.e. x0, x1, x2, and those correspond to each time step. Okay, so our dx by dt is xn plus 1 minus x of n divided by our time step delta t. So remember, delta t is called our time step. We're not using h's anymore. We're using notation that's specific to the problem we're interested in. And what we're doing in this problem is we're discretizing time. Let me just draw a little timeline there. There's our time axis, and we're chopping time up into little chunks of delta t. So delta for change, t for time. It's a much more appropriate notation, and that's what I want you to get used to using and get out a little bit of using h all the time, which is sort of an introductory way of doing things. But we also know that the accuracy of this, because we derived it from Taylor series, and it's ordered delta t. So the first thing we know about this scheme, this is forward Euler which is this bit here, and the final bit, the delta t, it's first order accurate. Okay. So we can quite quickly, because we've done Taylor series analysis on this, know that the accuracy of the thing. So what I just say is, whilst we're here, just pick up on the notation. So x is at a certain value of n. So we've got our x variable at t, and we're sampling it or trying to evaluate it at different points on the t-axis. So our first value of x would be x0, second one would be x1. More generally, we're looking at xn and xn plus 1. Okay, that's the first thing. So subscript n, we're using the subscript for the x value, and then we've got delta t is our increment in time. It's our time step. So delta t, remember, is the time step. Now, whilst all this may just seem to be details, getting our notation and our nomenclature, the words we use right at the beginning, causes all sorts of prevents all sorts of confusion further down the line. So we're using the subscript. We've got delta t, and it shows when you're presenting the solutions to me, if you're using the right notation and you're presenting it in the right way, it shows me that you understand this subject rather than just fumbling through the subject. So you know, it's you know, this is a really good place to start. So this is accuracy. So is first order accurate, so not a huge amount of accuracy, and that's all because you're differencing between step n and n plus 1. But what about the stability? So you may have done this exercise with John Thuban maybe more briefly, but I'm repeating it because I'm trying to emphasize these two ideas of accuracy and stability that are going to come up as we go forward through the material. Okay, so we're going to consider now, stability only means something when you've got a true solution, right? And then it only means in terms of certain context. So we have to define a specific f to which is our exponential decay, which is what we talked about before. Remember, lambda is a positive constant. We need to define that again, and we get that. So, and the truth, so dx by dt is minus lambda x, and the true solution is x star is the initial value of x e to the minus lambda t. Okay, so we're going to use that example again. And this is an example that I showed you pictorially before, but now we're going to just do it algebraically. That's the true solution that we've covered before. Now, if we do the forward Euler solution, of dx by dt equals minus lambda x. We then have the left hand side becomes xn plus 1 minus xn. You don't need to put the order in anymore because that's just, we've talked about the accuracy. And then we have minus lambda. Quite importantly, this is xn. And let's just pause on what we've done there. So we discretized dx by dt here by differencing between n plus 1 and n. Got the constant lambda, and then we got the x at step n as well. And it's key that it's at step n rather than another step. Okay, so it's the existing or the previous time step, depending on how you're defining things. Okay, so that's very important that is at step n. Okay. So we can quickly rearrange this. Let's do it in one more step than in the lecture notes, but we do xn plus 1 minus xn, so multiplying through by delta t is minus lambda delta t. So for our purposes, we just consider delta t and lambda fixed for this algebraic manipulation. Times x of n, and that finally finds that we have us making xn plus 1 over one side equals 1 minus lambda delta t on xn. So this is a sort of the most easiest one to rearrange and manipulate, but we get some very important principles here. We get that, so we've got the new time step in terms of the old time step, but we've got this multiplying factor here that takes us from the previous time step to the new time step, and this is called the amplification factor. called A. So A in this case is simply 1 minus lambda delta t. Okay, so you may have probably derived something similar last year, but I'm bringing you back to this just to emphasize this important points of this derivation that we're going to then apply to other cases. So we've got this thing called the amplification factor, 1 minus lambda delta t, and this is key to stability analysis. So what we're doing is we're doing here, let me just write it out, is we're doing stability analysis. Strictly speaking, it's numerical because there's other sorts of stability analysis in applied mathematics. This is a stability due to the fact that we discretized the equation. So we've got numerical stability analysis, and the key to numerical stability analysis, certainly in terms of the algebra, is finding this thing A. What is A? What is the amplification factor A? And then once we've got A, we can then deduce things about regimes of numerical stability. Okay. So this is very important. In fact, let me get the red thing out and really underline this amplification factor. Very key. So if you did this in how you did it in passing last time, or didn't really reinforce it, now's the time to really make note of that aspect of this calculation. This amplification factor is key. So in any stability analysis, the first thing you want to ask is, what is A? How can I calculate the amplification factor for this problem? And then the next step is to make inferences from it, which is looking at different categories of values of lambda and delta t. Okay, so maybe an old bit of algebra, a very quick bit of algebra, but really emphasizing again what, I don't apologize for revisiting it because it's sort of what I really want to sort of get ingrained, these ideas of stability and of course accuracy. Okay, so let's go back to that. So A is 1 minus lambda delta t. So what we now do is consider different regimes of the quantity lambda delta t. So this could be because of different things. You could be just you could be fixing lambda, that might be a fixed problem, part of the problem you're solving, and varying delta t, your time step. So quite often you find that the stability improves, doesn't always, with decreasing delta t. So that's one way of looking at it. Or you could do it the other way. Fix delta t and vary lambda. And remember, both lambda and delta t are real and greater than 0, okay, by definition. Okay, you can't get a time step of 0. It's impossible for a numerical method, and lambda is greater than 0 in our problem. Okay, so we're going to consider those different cases. So I'm actually going to go back now to the board, sorry, to the slides, and then consider these different categories. Okay, finish up. So in fact, let me just write up what A is at the top of this little slide here for remembering what it is. So A equals 1 minus lambda delta t. So if we make lambda delta t less than 1, that means that A is between 0 and 1. So A is less than 1, And remember, the way to think of application factor is this factor that the solution is multiplied, x is multiplied by each step. So that means the numerical solution is multiplied by the amplification factor that is smaller than 1. This means the numerical solution will decay, right? And remember my qualitative picture of numerical stability of the numerical solution shadowing the true solution. The true solution decays as well. The numerical solution decays. It might not be perfectly accurate, but it will shadow the true solution. So the scheme is stable for this case. Okay, so the accuracy is kind of a universal thing. The stability is for certain cases, right? So for this exponentially decaying case, we have to reevaluate things when we have to go to an oscillatory case, which we'll look at later. Okay, so that's the thing about this stability. So lambda delta t is great, and this makes sense if you fix lambda, which is maybe something from your problem, and just make delta t small enough, then you've got a stable solution. And that kind of makes sense because the amount of computational work required for this regime is greater. So, but that's more stable. I just want to jump to the bottom line and then we'll go to the middle case because I think it makes more sense. If now lambda delta t is greater than 2, a is less than -1. So this means at each step you're multiplying through by a. It's a negative number, so you can oscillate. Remember, this is quite a common feature of numerical instability. It oscillates at each time step, and it grows because a is less than -1, and the steam is stable. And again, it's working out that if delta t is larger than a certain amount of value, it's too large for the problem, then it's going to be unstable. And then the second line is the in-betweeny case where a is between 0 and -1. This means that lambda is delta t is less than 2 and greater than 1. It means that a is negative, but its modulus is less than 1. So it will oscillate in sign, but it will still decay with time. So it's, strictly speaking, by my shadowing criteria, sort of picture, it's stable, but it's not very accurate, and it's not a very useful solution. Instead, it's oscillating. So those categories may seem a little bit abstract. Let's just look at some pictures. Just getting the So we've looked at the stable case before. Lambda delta t is less than 0. It's the one I gave you back in the numerical instability. So let's just consider the two cases where it's sort of not so stable or completely unstable. So lambda delta t between 1 and 2, that means that a is negative but less than 1. So that means that each step the sign of the solution changes, this black line. So, and the red line here again, remember, is our true solution, but it still does decay. So it's not a very attractive solution, but it is at least asymptoting in the same way as true solution. So by that definition, it is stable. But the worst case is when the lambda delta t is greater than 2, oscillates, and I've had to blow up the x scale here to fit the solution in. That's how unstable it's getting. And it's starting off oscillating, and it's getting larger and larger until by time 3 it's oscillated. Its value is 60, where the true solution is very small. So this is analogous to that recursive example we saw where the true solution and the numerical solution went very different. But this time it's anchored in a full or ODE problem. Okay, so this is our first ordinary differential equation example of instability and accuracy, and we're going to carry on this sort of analysis with a full range of schemes as we go forward. So just one thing about this scheme is, if we go back to these things, we have conditions on lambda and delta t for stability. So one name for this is that this is conditionally stable, i.e. the conditions for stability are these guys here, these top two cases. But really the top one is the ideal. Okay, so if you make delta t, if we make delta speed, basically we want to make make delta t sufficiently small for stability, yeah, and that's what the top state is. So that's a very useful take-home message from this video. Okay, so that's enough for this video. Let me just stop now and see you next time.